Okay, this is our process selection route of methanol production. Okay, the process description is we need to produce 150 metric ton per year of methanol. The purified methanol should be at least 80%. Inlet for natural gas we use 164 million ton per year, which will produce 150.13 million ton per year. This is the unit that we use in this methanol production. The first unit is desulfurization. Desulfurization is to remove sulfur and avoid poisoning of reformer. The assumption is 100% of the sulfur will be removed. The second unit is steam reformer. Steam reformer is to convert water and methane into pure hydrogen and carbon dioxide. The third unit is autothermal reformer. Its function is to producing gas which will be needed during synthesis of methanol. The fourth unit is methanol synthesis. Methanol synthesis is to convert gas leaving from autothermal reformer to crude methanol. And then after that is flash. Flash is to separate liquid and vapor product. And the last unit is distillation column. Distillation column is to increase the purification of methanol. The small unit that we use is compressor, heat exchanger, and pressure relief valve. Compressor is to increase the pressure of the stream into the reactor, which the assumption is no change in size of pipe, there's no change in velocity, and also no changes in elevation. For heat exchanger, heat transfer from one metal to another. The assumption is water in vapor form is used and the efficiency is 90%. And the last is pressure relief valve. Pressure relief valve is to protect pressure vessel and other equipment from being subjected to pressure that exceed their design limit. This is the process flow diagram for desulfurization. Desulfurization temperature is 365 degrees Celsius and the pressure is 32 bar. There are compressor and heat exchanger before the desulfurization unit. For the energy balance calculation, the Q which is delta H is 117,790.4491 kilojoule per hour. And the calculation for heat exchanger, the mass flow rate of H2O is 0.9698 kg per hour and the mole flow rate of H2O is 0.05383. For the compressor temperature is from 1 bar to 32 bar. The work shaft, from the compressor we will obtain the work shaft. The work shaft obtained is 0.00164 kilowatt.
Okay, next I will talk about the steam reformer. Steam reformer have two compressor and one heat exchanger and the unit itself. So for the steam reformer unit, heat needed is 130835.725 kilojoule per hour. For heat exchanger is negative 3082.59 kilojoule per hour. Negative means that heat loss from the heat exchanger to the surroundings, so we don't need to calculate for the for the electricity. For power for the first compressor is 0.007454 kilowatt and power for the second compressor is 14.17547 kilowatt. Typo here. Okay, next is autothermal reformer. Autothermal reformer have one heat exchanger and compressor at stream 7. Heat needed by the autothermal reformer is 16,162,473.5 kilojoule per hour and heat exchanger is negative 996.504 kilojoule per hour, which is exothermic, same as steam reformer, and power needed for the compressor is 0.000248 kilowatt.
Hi, so I will continue explaining about methanol synthesis, but before I explain about it, so I would like to mention for the I will use the compressor to increase the pressure, because as we can see here in the input we have it as 41 bar, and in the output we have it as for the 82 bar. So we use the compressor to manage it, to make sure that there is no explosion or damage in the pipe. Also we use the heat exchanger to decrease the temperature from 1550 to 240 degrees Celsius. So methanol synthesis is a reactive process that we need to do the energy balance for each component, and to the calculation for the energy into the output. So as you can see here we use the reference as 25 degrees Celsius and 1 atom, because it's because it's a reactive process. Then we converted it to find each heat or energy. As we can see here, we use the constant for ABC and that because we are dealing with ideal gas, so we need to use that formula. As you can see here, we find it as appear H1 to H15. We find the Q as a negative value. That's because it's exothermic, and that show us its loss of energy. So now we continue with the flash. Before that we use a pressure valve to reduce the pressure, because the input is 82 bar. We reduce it to 40 bar. So the flash is non-reactive process. We calculated from another journals, because we're dealing with ideal gas also, and we need to separate it into a stream of vapor and a stream of liquid. As we can see here, the output containing the same component but in different phases. So we use the formula that shows how to calculate the ideal gas by our constant, which is A, B, C, and XY. As we can see here, we calculated using this formula to find the difference between V over F. Then we use the inertia constant that help us to calculate the difference between pressures and the energy balance. So as we can see here in the inlet, we choose the reference of the inlet. So we change so we make 0 for the CH4 and CH3OH, which is methanol. After that we converted it to liquid. We converted to a liquid phase to calculate the energy for the output of liquid, and we find the difference between temperature, pressure, and the boiling point. So here we can see a Q become as a negative. That shows that it's exothermic, and there is a loss in the energy.
So now we move to distillation column. First, there is a pressure valve, which is to decrease the pressure from 40 bar to 17 bar before entering the distillation column. And this is the energy calculation for distillation column. For For the input, as you can see here, this is the input and this is the output. So the purpose of this distillation column is to increase the purity of methanol as high as 80% purity. Thus, the input to the distillation column is in liquid phase, while the output is in both vapor phase and liquid phase. The one that we need is the vapor phase, which contain higher purity of methanol. And the end product or energy of the end product of distillation column is this amount, which is a positive amount, meaning the experiment is endothermic and it needs extra energy supplied into the reactor. And thus the energy required is 33,102 kilojoules per hour. So into costing, first we will calculate the cost for the compressor, in which for our system we have used 5 compressors, and all 5 of these compressors are of the same, which is for air shop at 200 psi compressor. So as we use the same compressor for all 5 systems, thus the cost for all 5 of it are the same. And for the water, cost of water, we didn't use water for compressor, so the cost of water should be 0. And we move on to the electricity. Since all the compressor need energy supplied, thus all the compressor need electricity as a source of energy. Thus there exists a electricity cost for all 5 of the compressor. Now for exchanger, for our system we have 4 exchanger. 3 of them are water heater and in large size. The function of these 3 is to increase the pressure, increase the temperature. And for the 4th heat exchanger, we use air-cooled bare tube area, which is to drop the temperature. Since all the energy is negative, which is energy release, thus there is no electricity cost for all these exchanger. And since all the heat exchanger use water, thus there is water cost for each of it. And this is the cost of the unit itself, which is 3. All these 3 is for water heater, which is large in size, and this is for the air-cooled bare tube area. And next we move to the costs involved for each of the unit. We have 6 units, and this is the electricity cost for all 6 units, and this is the water cost for all 6 units. And now we move on to the cash flow. The total capital cost is the total cost needed to produce or to buy the unit required. For example, heat exchanger and compressor. And thus, for our first and second year, since we didn't manage to start producing methanol yet, thus we should have negative cumulative cash flow here. And from the 3rd year, we will start producing methanol, and negative cumulative cash flow will occur for our first 6 year or 7 year, while on our 8th year we will finally able to obtain a positive cumulative cash flow, and thus we can say that we have achieved.
In conclusion, by feeding 163.99 metric ton per year of natural gas, our company can produce 150.13 million ton per year of methanol. The purity of methanol produced is almost 80%. That's all.